In this video, we're going to talk about how to integrate for product of inertia. Our previous videos basically gave you the background on product of inertia. I'm going to make 2 or 3 videos here just working different examples for how to integrate for product of inertia. And then we'll do several videos for product of inertia for composite areas. But again, this one is our first example for integrating for product of inertia. Even though product of inertia is a little bit of a strange animal, it's actually not too difficult to integrate for. And it's not as picky about the dAs as moment of inertia is, for reasons that you'll see. So it's not too bad, actually. So the common definition for Ixy is the integral over the area of x tilde times y tilde times dA, or you could say the integral over the area of x times y dA. Obviously, it depends on your definition of dA. If we apply the parallel axis theorem for product of inertia and define Ixy as the integral of dIxy, and we write the parallel axis theorem in differential form as dIxy is equal to di bar I prime di bar x prime y prime plus dA times x tilde y tilde. Since virtually any element that you choose is a square or a rectangle, then di bar for all of these guys is 0. And so basically the integral for area moment of inertia is just the integral of the dA x tilde y tilde term. So in other words, Ixy is the integral over the area of x tilde y tilde dA for any element, a dx dy element, a horizontal element, a vertical element. So you can pretty much do whatever you want as long as you define x tilde and y tilde correctly. So in this example, I'll work the same problem 3 different ways to show you. So this is a cubic area between the y is equal to 1/8 x to the cubed curve and the y-axis. And x is going to range from 0 to 4, and y is going to range from 0 to 8. So we want to find the product of inertia of this area. If I choose to take a horizontal element, then it's dy thick. It's x long. So the dA is x long times dy. But I'm going to convert the x to y. So the x is equal to 2y to the 1/3. And so I can plug in 2y to the 1/3 here for x times dy. My y tilde is y to the centroid of the dA. My x tilde, however, is the average of the x left and the x right. X left, of course, is 0. My x right is 2y to the 1/3. And so my x tilde is 1/2 of x, or 1/2 of the 2y to the 1/3, or y to the 1/3. So my Ixy then is x tilde, which is y to the 1/3, times y tilde, which is y, times dA. And if you multiply this together, you get 2y to the 5/3 dy. And we're integrating on y, so we're going to go from 0 to 8. And so if you integrate that, you get 192 meters to the 4th for Ixy. That's taking a horizontal element. If we say, okay, I'm going to take a vertical element, then it looks like this. The dA is 8 minus 1/8 x to the cubed dx. My x tilde is x. My y tilde is the average of y top and y bottom. And so it's 1/2 of 8 plus 1/8 x to the cubed. So when we set up the integral, Ixy is the integral of xy dA. So this is x tilde is x. This is y tilde. And this is dA. Now this is kind of complicated But you can do the algebra. You can multiply these guys out, and it's actually not too bad. So you get 64 minus 1 over 64x to the sixth. And then multiply x times that. And then you can integrate him on x from 0 to 4, and you get Ixy is 192 meters to the fourth. A double integral is even easier. So if you set up a double integral, my x tilde is x, my y tilde is y. I'm going to integrate my y from 1/8 x to the cubed up to 8. And then we're going to integrate my x from 0 to 4. And it's just as easy to do it on your calculator. And on the TI-89, I get 192 meters to the fourth. So, so this is an example of integrating for product of inertia. It's not too bad. It's just the integral of x tilde, y tilde times dA. You basically could choose any dA. You just have to choose the correct x tilde and y tilde. One of the two will either be x or y, and then the other one will be like the average of the two to get to the centroid of the dA. And this is just a reminder. The Hibbler on his crib sheet gives the general formula, the integral of xy dA. I gave the general formula as x tilde, y tilde, dA. Hibbler's definition is only true for the double integral. This is x, this is y. For a horizontal element, then the y will be y, but the x will be x tilde. For a vertical element, the x will be x, but the y will be y tilde. So neither my approach nor his approach is exactly true, except for the double integral, and his is true for that for sure.